All right, so we're going to talk about the math of curved mirrors and also I can do some examples of that. But let's get on the same page with some of these definitions here. So the first is focal length, right? You should already know what that is. That's the point where all rays that are parallel to the principal axis, right? They all cross there. R sub c, that's radius of curvature. Oftentimes just use r, right? A focal length, right, is half of that. Di is distance of image to the mirror, right? So the closer the image to the mirror, the smaller di is. Same thing for do, which is object distance. M is magnification. We're talking a little bit more magnification on the next slide. Okay. And hi is the height of the image, and ho is the height of the object. Okay. So let's talk about rules for positive and negative. Okay. So I got these two images here, right? Or these two setups here. So here's the thing. This side, the object side, is positive. Okay. So in this case right here, right, the object is always do is always positive. Right, I guess it says it right there next to me. Right, do is always positive. Right, I can't erase. That's interesting. It's really awkward. Okay, well, whatever. I can't erase. Do is always positive, right, because it's always on the object side. But di can be positive. So this one right here, this right here, this is di, and it's positive. And in this case, that's di, and it's negative. All right. The focal point can also be positive or negative. So this focal point, right, this f right here, this is positive, and this f right here is negative. Okay. All right. The height of the object is also always positive, and hi is positive. It's the same orientation. So we'll talk a little bit more about that in a second. Okay. But here are also the equations. So the first equation is, right, f equals radius of curvature over 2. Okay, always. Actually, the absolute value of f is the radius of curvature over 2, right? Because it's dependent on whether it's concave or convex mirror. Radius of curvature is always positive. The second equation, this is the big one. This is the mirror equation. 1 over f equals 1 over do plus 1 over di. That's the main one you're going to use in almost every problem. And one interesting thing about this is that for a flat mirror, f equals about infinity, right? Because it has no radius. And so if I put that in here, I get 0 equals 1 over do plus 1 over di, which means that do equals negative di, which is just exactly what we already knew, right? Which is that an image appears, for a flat mirror, the object and image are on opposite sides of the mirror, equidistant from the mirror. And the final equation is magnification. Magnification is hi over ho equals negative di over do. All right, so let's talk more about that magnification stuff. All right, so what does a I'm going to type this, insert. Type this so we can do it here. Text box. Okay. What does an m equal 2 mean? Well, this is going to mean the image is twice as big as the object. And, okay, well, we'll stop there. And we're going to add something to that in a second here. What does m equals 1 over 2 mean? Okay, then this means the image is half as big as the object. But if you look back at the previous slide, you'll notice there's this negative sign right here. So what does a negative magnification mean? So for example, what does m equals negative 2 mean? How is that different from m equals 2? The answer is orientation. So this image is twice as big as the object and upright. Right? The object and upright. The negative means it's flipped upside down. Inverted or upside down. And m equals 1 over 2 means that the image is half as big as the object and inverted. Okay, so that's what the negative sign means there. We have to have some way of like thinking about when we flip images upside down, because we know that mirrors do produce upside down images. All right, so let's do some examples here. Someone's got you got a football player's helmet. The helmet has a diameter of 30 centimeters. And what kind of mirror is the helmet? What kind of image do you see, and where is the image located? So first off, diameter of 30. So that means radius equals 1/2 diameter, which is 15 centimeters. And focal length is the absolute value, at least, is 1/2 radius, or 7.5 centimeters. Okay. Now, what kind of mirror is the helmet? I probably should answer that first. So if we're on the outside of the helmet, so here's my big helmet. It's kind of a sphere, right? And the image, the thing we're looking at here is the sun. The sun is our object, right? This is a convex mirror, right? It's not a concave, it's a convex mirror. So the answer to this is convex. And because it's convex, right, that means F is equal to negative 7.5 centimeters. What kind of image do you see? Convex mirror, right, always produces virtual image. Okay, convex mirror always produces virtual image. We saw that on our Dre diagrams. There's no other alternative for a convex mirror. If you look on there, it's always a virtual image. Now I know where the image is located. So I'm going to use, this is where I'm going to use 1/f, 1/do, 1/di. F I know, 1/negative 7.5 equals 1/do. And this is sort of interesting. Do is infinity, basically. Or it's not really big, but it's really, really big. The sun is really far away, right? What is we're looking at the reflection of the sun. Sun is super far away. As far as we're concerned, it's infinity. So 1/di. Okay. 1/infinity, that's basically 0. So 1/negative 7.5, 1/di. Di is equal to negative 7.5 centimeters. Okay, so that means the image is behind the convex mirror, which is, again, what we expect. All virtual images should have a negative di, because they should appear behind the mirror. Right? Okay. We've got 15 centimeter tall candle, 45 centimeters from the mirror, focal length of 30. And I want to know where the image is located and what is its height. Okay, so pretty simple. We go 1/f equals 1/do plus 1/di, right? And by this means, like, we've got like this mirror here, right? Here's the focal point. I'm just gonna draw an arrow. Here's the candle. All right, we know sort of what's gonna happen, right? And the center of curvature is here, the curvature. Right, we know the answer should be from our ray diagrams. It should be somewhere like that. The image is out here. So just be aware. We should expect the image to be tall, to be bigger, further away, bigger, and inverted. But let's see if the math matches that. So 1/f, 1/45 plus 1/di. 1/30 minus 1/45. Equals 1/di. You can do this in your calculator, or you can do common denominator, which is 90. So this is 3/90 minus 2/90. 1/di. 1/90 equals 1/di. Di equals 90. Okay? So we know it's out here. Right, here's my image. This is 90 centimeters. A little point of interest here is that, like, as you can use meters or centimeters for these numbers as long as you're consistent. If you're going to use meters, you have to use meters for focal length, do, and di, all of them, or you use centimeters for all of them. Totally fine. Now we do, what is the image, what is its height? So remember that magnification equals hi over ho, negative di over do. Well, I know ho, so I've got hi, ho is 45, no, 15, sorry. 15, that's equal to negative, right? Di is 90, DO is 45. So HI equals negative 15 times 2, negative 30. Or negative, sorry, negative, yeah, negative 30. Why did I think I got that wrong? Negative 30 centimeters. Okay, so in other words, we're saying the negative sign, right, it's inverted. We already knew that was going to happen from our ray diagrams. So that matches as well. All right, we've got a car. So you guys have all seen this. Car's mirror says objects in mirror may be closer than they appear. What kind of mirror is this? Okay, so first off, it's got to be a virtual image, right? We know this because it's upright. So, and you've all looked at a car mirror. Upright. And DI is greater than DO, right? We're saying that object mirrors may be closer than they appear. Okay, that means DI is greater than DO. The only way this happens is this is a concave mirror. But it's a concave mirror with a really big radius of curvature. Okay, I said 10. It's actually probably even higher than that by a fair bit, but I just said 10. So why not? So radius of curvature is 10. F equals 1/2 the radius, or 5 meters. DO is 10 meters. No, the image is 10. DI is 10 meters. Okay. And so I say 1 over F, 1 over DO, 1 over DI. 1 over 5, 1 over DO, plus 1 over 10. We do 0.2, right? 1 over 5 is 0.2 equals 1 over DO. I made a mistake. This is negative 10. I said it's a virtual, it's an upright image, which means virtual, which means this is negative. Okay, so negative 10. All right, so 1 over DO plus 1 over negative 10, which is going to be 0.2 plus 0.1, right? Because this is negative 1 over negative 10 is negative 0.1. We add to both sides to get 0.1. This is equal to 1 over DO. So this is, right, this is really 3 over 10 equals 1 over DO. And DO then is going to equal 10 over 3 meters. Okay, so 3.33. So it looks like it's 10 meters away, but it's only 3.3 meters away. And that's the example. This, like I said, this is not a totally realistic example. The radius curvature is going to be way more than 10 for a mirror. And that's going to make it so these two images get closer and closer. But that's the answer. All right, finally we get a one with a little bit more math to it. So you want to project an enlarged image. So this is a key thing. A projected image must be real. Okay? And if it must be a real image, that means it's inverted and a concave lens or concave mirror. Sorry, we'll do lenses later. Concave mirror. So two things we know. We know it's inverted, we know it's concave mirror. Always, projected images are real, they must be inverted, and therefore they must be concave. And again, if you look at your ray diagrams, you'll see the only images that are real are inverted plus concave mirror. Okay? All right, so what do I do now? Well, I've got 0.4 as my radius curvature. So F, the absolute value of F equals 1 over the radius curvature. Not 1 over the radius curvature. 1/2 the radius curvature, which is 0.2. Because it's concave, I know it is going to be positive, so I can say that F is positive 0.2. Okay? Now, this says it's 3 times the size of the object. 3 times the size means the absolute value of the magnification is going to be 3. But because it's inverted, we can say that the magnification is negative 3. Okay, so now I've got 1 over F equals 1 over DO plus 1 over DI. So 1 over 0.2 is equal to 1 over DO plus 1 over DI. Can't solve this equation. Two variables, two unknowns. I don't know. Okay. So I go, what about magnification 3? I get -3 equals, right, because it's magnification equals negative di over do. So -3 equals negative di over do. Again, two variables. But now I have the same two variables and I have two different equations with them. So I say -3 do equals negative di. That means di equals 3 do. I can plug that in here. So I got 5, right? Because 1 over -2 is 5 equals 1 over do plus 1 over 3 do. Okay. Common denominator of this thing. 5 equals 3 over 3 do plus 1 over 3 do. That equals 4 over 3 do. Cross multiply, right? Or multiply both sides of 3, so I get 15 do equals 4. That means do equals 4 over 15. Not my answer. All right. How far from the wall should we place the mirror? All right. We want the image to be on the wall. So I was really looking for di. Fortunately, I've got this. Do is 4/15. Well, di is 3 times that. So 12/15 meters. Okay. So you should be placing the mirror 12/15 from the wall, and you should be taking the object 4/15 from the mirror. And with that, you will get a image that is 3 times the size of the object. Okay. All right. Save this.